All right, if all goes well, you can hear me now?
Yes.
Good. All right. Get rid of that then. Okay. Next, actually, how does this sound compared to the normal sound? Is it okay?
Yeah, it's okay. It's not as good.
Okay. I'll try the other one. I think what happens after every time Windows does an upgrade, I have these. But okay. Well, the first exercise here is just to essentially the exercise we did was the ions, but in a U1 case. Another example of doing a Lagrangian. And the second one is one that Barry Holstein paper on, where you get out the frequency dependence of scattering of light off the sky with very little assumption other than gauge. Okay. So those are two things you can try in these exercises. Let me just remind you what we did last time. Here's the rules for effective. So the first thing you do is you figure out what theory you're trying to do by writing out the most general Lagrangian with your particles. You have a set of particle symmetries. You write the most general Lagrangian. With symmetries, particles, of course, and you order it by the energy. And the second thing one does is you then quantize it using the lowest order. When you quantize, you're able to put the loops, you renormalize. When you renormalize, you have to measure the parameters or determine them in some way. So you match or you measure. And all that's just set up. And then the last thing you end up having to do is calculation. And these predictions in general come from low energy properties. Because that's the only part that you really trust. Okay, so we're going to do that today. We go through this pathway in general. And in fact, we've done so much work in other settings that it actually goes really, really quickly. That we then have to talk a little bit about how you. Okay, so the one that's the question is, what do I mean by lowest order? In gravity, for example, this will just be the Einstein. Okay, you'll see we're going to have correction for the Einstein at higher orders of curvature. But those are the higher order corrections are much smaller when you look at the low end. So you start with the lowest order one. Add these corrections. In the chiral perturbation theory one we did, it was that lowest order had two derivatives in it, and then the corrections had four. It exists at the lowest order, at the lowest end. Okay, so you take your whatever particles you're wanting to build into your theory, in our case, gravitons. We take write out their Lagrangian, take the most important one, start there, you have in perfect. In this case, I mean smallest number of derivatives. In massive theory, we'll have massive player. Normally, it's the usual kinetic term, and interactions come in at that order. At the same order. So standard model, you'd have the whole standard model. But then there'd be higher powers that are beyond this model. Tree tells you it's perturbation, but you could also end up using them in loops. That's sort of the secret. So we just did the rules there. So let's do this for general relativity. General relativity, field theory. You're supposed to do is write out the time. Back here, the x plus e for x, squared of g. Then there can be a constant. There's the Einstein piece, which has two derivatives. Ordering this as the energy expansion, we would also then include four derivatives, C1 R squared plus 2 R 2. You might try thinking that there's a Riemann tensor if you knew alpha beta. This guy's redundant because there's this Gauss-Bonnet identity, which I told you about, which is 2 beta squared 4 R squared plus squared total derivative. So basically, we drop that guy. Then in the energy expansion, there'd be our cube terms. So there we've done step one. Now, before we move on, let's actually, we've seen some of these guys before. This guy is, of course, the cosmological constant. That has no effective field theory, doesn't tell us anything useful about that. I'm actually going to drop it from what I'm doing because it's irrelevant on the scales that I'm interested in. Ordinary scales here, it's so tiny that it's not relevant to the gravitational force we're dealing with. I will drop it. Interesting enough to keep it. The second terms, of course, are just usual general relativity. The third terms are curvature squared terms, and since we live in a world with small curvature, they're almost irrelevant to doing. And in fact, you can bound these coefficients. So let's see how you bound them. Okay. The curvature itself starts off like two derivatives on a fluctuation. So then our squared terms look like two derivatives h, two derivatives h of higher order. Okay. So if you were to take these terms seriously and do the equation of motion, the equations of motion would look like box H, which is the piece that we had before, weak field limit. And then the second term would be terms that would look like one of these coefficients and four derivatives. Various terms. And on the other side, you might have so this is a modification of Einstein's equation by four derivatives. This tells you then that the propagators, if I do an exchange, so like mu on one side, mu on the other, and with some tensor structure, 1 over 2 squared plus c to the so when would you see this? Well, 1 over 2 squared minus plus c q to the fourth can be done in partial fractions. This is 1 over 2 squared minus 1 over 2 squared minus m squared. And in fact, I actually know that the m has to be solved. Actually, m squared is proportional to 1 over. Have to solve for it. In fact, this is another exercise. But you can see that the coefficient out in front of the 1 over 2 squared is unchanged. When 2 squared becomes very small, 2 to the fourth, 1 squared to 2 squared. Here the 2 squared compared to m squared is small. So the 1 over 2 squared comes. In fact, you don't change the overall factor, which is good because then you change the Newtonian. This guy goes into then terms that look like G m 1 over r from that first piece, and the second piece is the power to the minus r. Okay. And so if you bound, you say that we know the gravitational force applied at a millimeter. Let's say there's this power here, but we know gravity works. Gravity works at a millimeter scale. Audio power. That then can be converted into a bound. That's the logic. This was done by Kelly Bell. Actually, I should probably post this because I haven't posted it yet. General relativity and gravity. It's actually is a classic in the this little corner of the community. But that then actually it turns out the tensor structure is a little bit more complicated. 2 Yukawas, not just one. Here the 2 parameters, but it basically looks. And I'll let you do your own bound, but the bound is worse than C being less than 10 to the 50. Okay, so this is a bad bound. It's actually many orders of magnitude worse, but I'm trying to do this as an exercise. Do it yourself. So I'm just telling you it's worse than that. Remember in chiral perturbation theory, we had these equivalent parameters, LIs. In chiral perturbation theory, they were 10 to the minus 3 or 3 times 10 to the minus 3. Here, these guys are essentially unconstrained. We have no physics that's sensitive to them. So there we've done a little constraining of it. Okay. Also in the Lagrangian, there could be other terms, which is also matter term, mu phi squared, matter minus 1 squared, phi squared, is matter Lagrangian. You could also have higher order terms here, which might be, for example, r phi squared. If we saw that one before in ensemble coupling, but there could also be others. 2 phi, and there could be another one, 3 r mu phi, that. Actually, this guy can probably be removed by equation of motion, but let's not bother. I'm not going to do much. Okay, but the matter part also has higher order. Okay. Okay, and these guys are essentially unconstrained also. They're basically the same sort of constraint. But these guys, if we wanted to modify a vertex, we have extra powers here. The typical constraint here would have an extra q squared at the vertex, and there'd be a 1 over q squared that gives you a delta function potential instead of a power, but it basically because we can't measure short. Okay. I should actually say that this guy here, if I take m big, is limits to a delta function. So that's step 1. So we go back up here. Step 1, we've got the most general Lagrangian symmetry is verged by the energy expansion. Quantizing we have actually did already. We did this by doing Cook development using the background field method. We then also did the one loop. We got 1 over 16 pi squared, 1 over epsilon, 1 over 120 r squared, 7 over 120 r mu, These coefficients, if I do scalar loops, we also got to work that out. 180. The next step is to renormalize. And you see that these guys look like C1 and 2. So C1 renormalized is C1 plus the 1 over space squared, 1 over epsilon. These guys, of course, come along with the gammas or pi's. Etc. C2 is 120 here. C2 gets normalized. Same procedure. 7 over 120. And that's about all there is to say there. The only thing I guess I need to point out is we're starting to see this energy expansion here also. It's even more obvious if I do show the two-loop result. Two-loop is two-loop divergence is in pure gravity. It's 209. 2880 1 over 60 pi squared 1 over epsilon, and then r mu nu alpha beta, r alpha beta gamma delta, r gamma delta mu nu. Okay. In this case here, we've said all terms that are like r mu nu r goes to 0 because that's the equation of motion for gravity. This is the Riemann tensor still left over. So we've seen here now that this energy expansion is the equivalent of Weinberg. Is tree level, well, do order p squared to r at tree level at energy to the fourth, which is 4 derivative r squared at tree level for r one loop. We used the lowest order Lagrangian one loop and got r squared. And then it keeps going. E to the fourth is like 2 loops. And e to the sixth is like 2 loops. So we have this power counting that fall out that you can see even in the divergence. So back up here. We've done step 1, step 2, step 3, step 4. We did using the bounds on coefficients. So now we're left to do the rest of the prediction. So we'll do my favorite example by doing the gravitational interaction, Newtonian potential. So the goal is to do the following. So then remember we previously got the Newtonian potential by exchanging a graph. That was the sea level. Now what we want to do is do loops. So what are the loops? Well, the Feynman diagrams where we know that one. That's the one graviton coupling. There's a coupling two gravitons to a scalar. There's a triple graviton coupling, so something like this. That's all. It actually needs a lot of diagrams. So let's do. Oh, and I've got the ghost. There's the ghost. We have ghost. Okay, so let's. Here's one that you might write out. Here's the vacuum polarization diagram. And that's one where we better put the ghosts in. So in addition to that, we have ghost. There's a vertex diagram that's this. There's the vertex diagram that looks like this. There's diagrams that look like that, plus the reverse. Boom, boom. I'll write this next one under here. There's one that looks like this, and with the triple graviton vertex. So I put them next to each other because the triple graviton vertex. There's one that looks like this. There's a box diagram, which is this. Cross box diagram. That. If I got them all. Let's see. I had to copy down the. There's actually is one more diagram. I'm not going to. It's zero. Like that. That's a massive graviton loop at the top, but it's like in dimensional regularization is effective. So I think I got them. Anybody see anything I missed? Okay. So we're going to sit here. We're going to calculate one by one. Yeah. So the ghost only couples up to the gravity part. It doesn't revolve to the matter. Okay. And it only runs in closed loops. So, for example, this diagram, because I'm circulating, that's coupled back to this. Okay, so there's what's to be calculated. At this stage, we actually let me give you the types of answers that we're expecting. So remember, we're looking mainly for non-local or non-analytic. So schematically, in momentum space, we have our matrix element that's going to start as 1 over q. So there's the moment, the leading piece. And I'm going to take this matrix element, I'm going to Fourier transform it and give you a V of R, which is Fourier transform. V of R M Q in the non-relativistic limit. So that's, so I'm going to look for corrections to this. B, let's do this in parallel. B has the 1 over R, let's all right, G M R. And there's also then 1 plus correction. Okay, well, in the coordinate space, when I actually know a couple corrections, I know that I get G M over R correction. That's dimensionless already. There's actually a C squared in there. C squared at this stage. Okay. That follows from the Fourier transform of something that looks like all. It looks like the square root of Q squared M squared. There's actually could be completely fair. Kappa squared G squared times Q squared over M. That's dimensionless. That guy Fourier transform to GM over. This is a dimensionless piece which we know. And so these guys I know are connected by Fourier transform. This is one of my non-analytic pieces. The next piece that we could imagine getting is something that involves H bar. So let's put G H bar over R squared. Cube that is, I'm pretty sure. This is down by another power, so linear in G, one loop. It's linear in H bar, it's quantum. It G over R squared is dimensionless. This guy, if you look at what a Fourier transform is, it's G Q squared log Q squared. So that guy's non-analytic also. And then you'd also expect that besides the non-analytic pieces, there's analytic pieces. Q squared. If you think about that guy for the moment, I've got Q squared there, Q squared in the denominator. That's Fourier transform to a delta. Those guys are paired. Yeah, I'm occupied as a cube. Thank you. And I've taken the non-relativistic element. Okay. So actually, we start to see what we're looking for. We've got analytic stuff that gives me something that I'm not interested in, the delta function. But I am interested in these non-analytic pieces, like the arguments I gave you before with the other effective field theory. These are signals of long distance travel. Okay. If I go back up here, I then have to pull up close to calculate those guys. And it's done it. Harry was involved in doing it. What can I say about it? Well, so the goal is to pull out the square root of q squared t and the log. And just to show you how you do it, somewhere down at the bottom I copied.
John?
Yes.
Question before we go on about the second non-analytic part and the Fourier transform. Where does the bar come from? Just in spirit.
Where does R come from?
No, H bar.
H bar. Okay. I'm sorry. What I did here is I'm in position space. I'm trying to write out dimensionless variables, and GM over R C squared is dimensionless.
Yeah.
If you put the units, GH bar over RC cubed is also dimensionless. The easiest way to see that, let's see, we know that GM over RC squared is dimensionless, and we know that M, let's see if I can, H bar C is 200 MeV Fermi.
So I understand how these quantities are dimensionless, but shouldn't they correspond to the Fourier transforms of the above?
Oh, there's probably H bars up there also.
Oh, okay.
Yeah, yes.
Okay.
Okay, so this, I think I've now got my argument here. GM over RC squared. H bar C is MeV Fermis. MC squared is MeV. Fermis is R is Fermis.
Yeah.
So this then GM
right
over R squared C cubed has the right dimensions. We just, when we do the field theory calculations, no one ever carries their H bars. So I'm just taking the logs, and if I had to put powers back in there, of course it would work out. Has to work out. Is that enough of an answer?
Yes.
Okay, good. Good. So the point of this table here is just to say that we know how to pull out logs and square roots from these things. L in this table, L is log q squared, and S is the square root of q squared minus square root of minus q squared, actually. Minus q squared over m squared. Let me just check down here just to be sure I got. Oh, there's an extra pi squared. Sorry. S is pi squared in it. Okay. So it takes some work to get these formulas out, but if you just are doing these formulas, you start seeing that in particular, let's look at the S for the moment. You need, you always, all these have two masses propagators in them, ones that I'm showing you. They all give logs of masses. Anyway. So, what else to say? Except that it's a long calculation that you really don't want to do. The answer when you get done with it is the effective V of R is G M1 M2 over R, 1 plus 3 G M1 plus M2 is symmetric over R, and then plus 41 over 10 pi squared G over R squared. That's the H bar one. Okay. So lots of various things to say about that. So there's the answer. This is the quantum piece. This is a classical term. Potential. So many things to say. First thing to say is, what about C1, C2? So remember, C1, C2 is analytic. These are analytic terms. And so they go only into the delta function. They don't influence the log. So we sort of knew ahead of time that they weren't contingent because we were after the square root of log. And it's easy to see how it happens if you imagine doing vacuum polarization, for example. There's the vacuum polarization, or we're just putting in C1, C2 as a pair term. So here's the little C1, C2. Remember, the vacuum polarization renormalizes C1, C2. The divergences go into that. These both go like 1 over q squared from the upper propagator times q to the 4th, because there's C1, we have 4 derivatives, times 1 over q squared from the lower propagator. These things go in as a constant then, which then, as advertised, puts them into the delta. Okay, also, there's some more divergences that we haven't seen yet. This guy is divergent. It's right here, there's a divergence there, there's the 1 over epsilon there. But that divergence goes into the local piece, which was like my D1, D2, D3 term. So those are that's again local. So it goes into a local term, which is the D1, D2, 3 pieces. They're analytic. They go into the delta. So put a lot of boring stuff into delta. The other thing to say, what's the next? Well, maybe I could focus on the classical. A classical term is the type of term that does corrections to the precession of Mercury. So all the classical tests using the post-Newtonian expansion. So this is the post-Newtonian expansion. Of general relativity. And so these type of terms are expected also. But what we saw actually is sort of funny. we got a classical piece out of a loop diagram. So how do you get classical pieces out of loop diagrams? Because normally you see textbooks saying that the loop diagram loops is the H bar expansion. But that's in fact not correct. So you can get classical physics out of loops, and here's a perfect example. And the flaw in it is there are parameters inside the Lagrangian that depend on H bar. And so, for example, if you have the Klein-Gordon equation, Klein-Gordon Lagrangian, wrote it out again. Mu phi squared half m squared over h bar squared phi squared. But normally doesn't write the h bar, but it actually goes right there. It's 1 over h bar. And so the extra factors of the masses can actually bring in inverse powers to h bars, and that's exactly what happened. The piece that we were looking at, gm squared q squared over m, has a 1 over h bar from the masses. It cancels the h bar that normally comes from the loop and tissue comes back. So that's what it. Yeah, so most of the time, I have to say, most of the time you do get the h bar count time close. There's a small set of cases, and so in fact the standard reference on this is not surprisingly it's people room, myself, and Holstein. We have a PRL. 2004, I think. I'm going to put a question mark on that, Barry. I don't know. Somewhere around. Look up these to find. Look up Donnie and Holstein and classical loop, classical flexor. Yeah. So I was thinking maybe next time I'll do another one of them where we can actually see why it failed. But let me do the why it fails here also. Actually, I'll build up the insight. Right. So the other example is actually a photon loop, but the diagrams where it fails are particularly this guy. And what I think of that is you've got this upper line here is a massive particle, and it's got a gravitational field around it. What you see going around it is a gravitational field. Part of that is a classical gravitation, and then you're hooking up to that with a T mu nu. You're measuring the energy contained in the classical gravitational field around the particle. That's going to be the interpretation on the other example. I'll do photons, will be classical electric field. Okay. Actually, while I'm here, it's also sort of interesting to see where this comes from. So when we do this, you'd say, well, what's the important contribution? The funny thing is they're all over the these two here, some units. This is plus 43/15 comes from those two diagrams, the ghosts and the graviton. This vertex here and the one underneath it, as I've grouped them together, those guys is -42/3. Okay. Opposite sign, 5 times bigger. Then the box and the cross box combine up to 94/3 with a plus sign. This guy here is +45 in the same unit. Enormous. This guy is -56 in the same units. That includes this guy up here also. And this one's 0. This one you knew ahead of time is 0 because heavy particles don't propagate very far, so they don't give long distance propagation. So the fact that you're coupled up to the heaviest particle, you know how to do it. Okay. So there's no rhyme or reason to these guys. These numbers are probably gauge dependent individually, but there's something gauge independent. But still, it's not like you can take just the vacuum polarization diagram and find a perspective. All these guys are. Okay, good. So, any questions about that? This is in some sense is a full calculation of feeding general relativity, the field theory. I will often say that this is a low energy theorem of quantum gravity. I have to write that down. Because the logic here is that there is presumably some high energy completion that makes it work with the theory of general relativity. Its information is embedded in those T1, T2, T1, T3, the coefficients there that determine the higher order. But it doesn't change the Einstein-Lagrange action as long as that high energy theory limits down to Einstein at the lowest order. These couplings and these particles are going to be the ones that are relevant to low energies, and so the long distance stuff is unique because any high energy completion of gravity is going to be. Let me do something a little different next if there's no questions about that. Let me talk about infrared photons and this is the title of a paper by Weinberg. This I have put on the site. It's PR Physical Review B576, 1965. It's a classic old paper on infrared properties, both of QED and of general relativity. So here's the setting. So basically, field theories have infrared data. Both in loops and and radiation. So first type are soft divergences. So these come when you're doing loop processes with very low momentum, and it comes from radiating a very light photon gravity. Okay. And the second type of divergences they have are collinear divergences. So in this case, the typical process looks the same. You're radiating an extra photon or graviton, gluon, but here these are almost collinear, but they're not soft. So for example, if a gluon splits up into two hard gluons, there's a collinear divergence as you integrate over the phase. So the close hard. Okay. Gravity is actually a better behaved theory than Yang-Mills in this. Gravity has only soft divergences. This is part of Weinberg's work here. The first one to point that out. If you do other theories like Yang-Mills, QCD has collinear also. And QED would have collinears if the charged particles were mass. The mass of the electron. You don't see it in text in the early course because the mass cuts off. But Yang-Mills where the gluons couple themselves to it. And here you could imagine that the gravitons coupling gravitons also have collinear, but they don't. And they don't have a good reason why. I think this is actually interesting. I asked Corey this when I was visiting Michigan, and he said he thought that maybe it was because photons and Yang-Mills have dipole emission and gravitons have quadrupole emission with vector 0 for direct quadrupole. Right, so it's quadrupole. So it's crisis suppression for it. Okay, that's sort of the logic. Come on. So quadrupole. Quad, move, oh, I don't know the right answer. It doesn't have to be spelled right. Okay. So that's part of it. But then, so Weinberg does a couple of things in this paper which aren't critical. He shows, of course, that the soft stuff cancels in both angles of gravity, and then he does there's a Coulomb phase for photons, and there's a Newton phase then for gravity. Let me just tell you a little bit about these guys. For soft emission, we can factor things in the following. So let's imagine we have a diagram of that. So this guy is A, and it's very soft. This guy right there is then going to be this P, this P plus K sitting there. So if the final state radiation, the propagator is P plus K, very close to the mass shell. For an initial state radiation, here's K. This guy's momentum, the initial state particle, would be E minus K, taking K away from the initial. So the factors that you have for photons, let me do scalar. The numerator here would be P plus K plus P, or P minus K plus P. So Weinberg writes 2P plus eta K mu is the current there, the P. What's downstairs is P plus eta K squared minus M squared. And since K is very small, we're just going to write M0 out in front. M0 is whatever that is. And eta is plus or minus 1, depending on plus 1 outgoing, minus 1. Okay. When you square this, P squared cancels M. We're going to drop K squared because it's very small, and get then M0 times P mu over P dot K and eta. So there's the vertex. We do the same thing for gravity. It's kappa 2 M0 P K Q K eta 0 2 over P plus eta K squared M squared is P M0 eta P mu over P dot K. Okay, that's basically just two indices instead of one. And so the matrix element for this is in the sum overall, the particle pi, the M0 factor out front, eta I pi 2 pi dot K. And you can basically then calculate the whole thing in terms of mu nu in this sum. Just there's the momentum. Okay. I also didn't say that I've dropped that K. There's two reasons. One is it's small compared to T, and two, K dot epsilon goes to 0, but basically dropped. Okay. Then the vertex directions have the same sort of factors. So let's look at a vertex direction here. Here's T prime. K there. As K goes to 0, this is likewise it's E type 2P. And this propagator is minus 2P dot K. Then I get my usual vertex. And on the other side I get E type 2 prime over 2 P prime dot k. So the basic point is I get the same factors. And if I'm doing gravity, I basically just put P there. So the momentum factors. At this stage, the proof of cancellation of self-divergence for QED immediately goes over to general relativity because basically we've at this stage, or he's at this stage already shown that the factors are universal instead of one factor of p or two factors of p. So it cancels in both QED and in GR the same way. Got the radiative section to one vertex, and then from cross section to cross section, from cross section square, cancel off the radiation, and the factors work out actually both 3D and of course he shows that so all orders, and I've only claimed the one order. He works all orders because basically the soft factors that initiate and then all orders. Let me just take a quick second to do the Coulomb phase. These come from a different set of diagrams. So here's my hard scattering. This guy looks hard. I can then exchange between the two legs an infinite number of soft dots. So those guys carry in those loops. There's places where they carry almost no momentum. Okay. If you do those calculations, you start finding divergences. In the photons, these go like one over the velocity. They exponentiate. Let me just write the answer for in the exponential form first. It looks like e to the I or pi. It's E1, E2, so those are the charges from the two legs. Beta 1, 2 is the velocity between the two of them. And there's a log lambda where this log lambda is put in here as a right cutoff. Like a photon mass. Put a photon mass. But this beta 1, 2, these are recognizable by the inverse velocity descent of them. If you do gravitons, as far as I know, this is primary paper is the first place that either of these correct. Coulomb phase, but there's equivalent minus I G M1 M2 over beta 1 2. And there's the funny beta factors 1 plus beta 1 2 squared. One minus beta 2 squared. I mean 1/2. 1 2 log lambda. So these guys cancel when you square amplitude, so that's why these there. they also can be cured. Could be cured by using not plane waves, but by using true Coulombic waves. So this is an indication of the fact that photons are long range. These things feel a long range force, no matter how far apart they are. It really should be used Coulombic waveform. So there's a long physics. Let me end there. Okay, good. We'll come back. We'll do a few more things in the effective field theory.